Hello everyone, in this video I will show you how to configure STM32 microcontroller, which is ARM CORTEX M4 based microcontroller, and you can see here I am using STM32 Discovery board, which is one of the most popular development board provided by STM32 guys. So in this video I will show you how to configure this microcontroller to output its internal high frequency oscillator of 16 MHz to its MCO pin or microcontroller clock output pin 1. So let's get started. Here you can see I already outputted 4 MHz square wave signal out of MCO pin. I captured this using my logic analyzer, which is a cheap one. You can see over here, which can only capture up to 8 MHz. So I cannot show you the 16 MHz. Maybe I will use my Handtech digital storage oscilloscope for that purpose in the future video. So let me explain the code. To output this clock, we need to first configure RCC CFGR register. So here you can see I am enabling the HSI clock source. If we go to the data sheet, in the reference manual, we can go to the section called reset and clock configuration. Here you can select the RCC register. Here I have selected the RCC register RCC CFGR. In this register, we need to configure this particular bit, which is MCO1. So we need to enable that. So if you take a look into that bit, it says that if that bit 21 and 22 bit value is 0, the 2-bit value is 0, then HSI is selected. If it is 1, LSI is selected. If it is 10, the high frequency external is selected. So obviously HSI and LSI, both of them are same. Here you can see in the STM32 board, I have an 8 MHz crystal, but I am not going to use that in this video. Instead, I will try to output the HSI, which is apparently running 60 MHz. So I need to put that bit to 0. Before that, here you can see some macros, which is basically the base address of RCC register. So where do I get this information? Once again, we can refer the reference manual for that. In this reference manual, we go to the section called memory map. So here you can see memory based architecture, then section 2.2, the memory organization. So obviously there will be a memory map. So here if I search for RCC, you can see the base address is 0x40023800. So that's also I created a macro for that. What is the use of this base address? I will tell you that now. If you know the base address, then you can derefer to the other registers inside RCC register. For example, like I said, we need to configure this RCC CFGR register, RCC configuration register, whose base address is 0x08. So basically, if you need to access RCC CFGR, you only need to add this address offset 0x08 to the base address of RCC register, which is obviously 40023008. This goes same for GPUA base address to GPUA. I will tell you why I choose GPUA, because this microcontroller clock output pin or this MCO pin as mentioned here, this pin is actually GPUA port A's 8th pin. So we need to configure some register related to the port A. That's why I am giving here the base address of GPUA2. Like I said, we are using HSI. So obviously, first of all, we need to set this bit to 0. I already did that. Here you can see I am first I clear that 2-bit, this 21st and 22nd bit using this simple bitmap operation. That will do just fine because we don't need to set any other value, because the value we have to give is 00. Once we clear that 2-bit, it's done. Like I said, my logic analyzer could only capture up to 8 MHz, so I cannot output this 16 MHz clock directly to the logic analyzer. It won't read it. So I need to obviously use the prescaler. There is a prescaler for this microcontroller output, clock output. To configure that, you can again use this RCC clock configuration register. Here there is this 3 bits starting from 24 to 26. We can use that to configure the prescaler MC01 prescaler. So I am going to first choose this prescaler as 4. That's why I need to put this value 110, which is actually 6, into this register. So if you take a look at the code, first of all I cleared that 3-bit starting from 24 to 26. Then I shifted the value 6 to that position. So that's it. That's why we get 4 MHz clock signal. Then moving to the next section, which is related to the GPUA register. If you take a look at the data sheet, this is not the reference manual, data sheets, the functional overview section, you can see that our GPUA ports, all GPUA ports from A to I are connected to AHB bus, advanced high speed bus, which runs up to 168 MHz. For enabling anything in Cortex architecture, ARM CORTEX architecture, if you need to use a peripheral, first thing we need to do is we need to enable the clock before configuring any other register related to that. So I need to configure this AHP1 clock for port A. To do, first we need to enable that clock. For that, again we can go to RCC section. So if we go to this reset and clock configuration for STM32F405 and 407 section, there RCC register section. In that, if we go to RCC AHB1 peripheral clock enables registers. So if you take a look at that register, RCC AHB1 peripheral clock enable register, we can see to enable the clock for GPUA port A, we need to configure this bit, the first bit on this register. Obviously, again we need to use the address offset 30. I already did that here. So if you take a look at this pointer, I am actually adding the RCC base address with the offset of this RCC HB1 ENR register, which is 30. So I am not going to explain that step for every other register. It's the way we access it. So it's basically which value I need to do. From the code itself is clear that I need to set the result. Let us confirm that by looking at the datasheet. It is the 0th bit. So if you go below the datasheet page, you can see to enable GPUA, we need to set 1 to that bit. Then only we need to start configuring the register related to GPUA. Once we configure, we need to move to the other register related to GPUA port, which is obviously the first register we need to configure is which mode this port should work. If you take a look at this clock output capability, we can see that we can output the clock through this MCO 1 pin, microcontroller clock output pin 1 or microcontroller clock output pin 2. The microcontroller clock output pin 1 is PA8 and clock output 2 pin is PC9. So I am using a PA8. So we need to configure that functionality. Basically, in case of a GPU port, it can work on 4 different modes. One is input, another one is general purpose output mode, another one is alternate function mode, and the last one is analog mode. We need to configure the port in analog function mode. For that, we need to configure this particular pin, which is used for outputting the microcontroller clock output, which is PA8. Let's take a look at that bit. The bit corresponding to the PA8 is the 16th and 17th bit. To enable the alternate function mode, we need to set a value of 10 in binary or 2 in decimal or hexadecimal. If you take a look at the code, first of all I clear that to be starting from 16 to 17. Then I set the value 2. And the final step is to configure the alternate functionality register. So we need to select which alternate functionality this GPU should work. So if you take a look at the datasheet section of general purpose input GPU functional description, you can see that 15 alternate functionalities. So a pin can be configured either in either of these alternate functionality. But remember, every pin don't have option to set all this alternate functionality. Some of this alternate functionality will be available to it. So to set the microcontroller clock output, we need to set the alternate functionality to AF0. So if we take a look at the data sheet once again, we need to set this GPU alternate function high register which contain the configuration bit for pin 8 to 15 and GPUA alternate function low register which contain the bit for pin 0 to 7. So in our case, since we are going for the pin PA8 or the 8 pin in the port A, port A, GPU port A, we need to focus on the first 4 bit starting from 0 to 3. We need to set the value 00 for selecting the alternate functionality F0. So obviously the only thing we need to do is clear that 4 bit. So here you can see I did the bit math operation of AND operation to clear that 4 bit. Once you did that, you can upload the code, it will work. So here you can see I already configured for 4 megahertz. Let me conclude this video by showing you how to configure it for getting a frequency output of 8 megahertz. So let's take a look at the prescaler. In this case, I need the prescaler of 2. So the 16 megahertz clock will be divided by 2. Then I get the 16 by 2, 8 megahertz. To do that, I need to set the value 100 or 4 in this 3 bits starting from 24 to 26. So I need to shift the value 4. So let me go to that register over here. Instead of shifting the value 6, I need to shift the value 4 as per the data sheet. Here you can see 4 is 4 division by 2. Once I did that, I can save the file, then right click the project, debug as. So 0 error, 0 warning. Now it will try to connect to the debugger. Yeah, debugger is connected. The ID is switched to debugging mode. Then I can run. Then I will go to the logic analyzer, then start capturing. So you can see I get some data. So let me check the frequency. Obviously you can see it's 8 megahertz. If you look at the left side, you can see it's 8 megahertz. Okay, that's how we configure it. I hope you understand content of this video, and thanks for watching. I will see you next time.